Hello, chemistry. Today we are going to talk about the ideal gas law, which I alluded to a little bit in class earlier today. The ideal gas law covers gases which we consider to be ideal, and an ideal gas is one that obeys all of the gas laws that we've been talking about. Now, so far, basically, if we tell you a gas is in the ideal gas law, you're going to just go ahead and assume it's an ideal gas. In a later lesson, we will talk about what makes up gases and why gases sometimes behave in non-ideal behavior. But essentially, the ideal gas law is going to go back, if we go back to kinetic molecular theory, that all of the assumptions of kinetic molecular theory are true. So when we think about gases, we think about the four properties of gases all together. P, V, T, and N are all brought together. And if you remember, we had the relationship between pressure and volume was an indirect relationship, inverse, so they're next to each other. And we had the temperature in the denominator because the pressure and volume were both directly proportional to temperature. And then in the last lesson, we learned that the volume and the number of moles were also directly proportional. And so that goes down in the denominator as well. And as before, this equation or this function is equal to a constant. But now we have all four of the variables in the equation, so there's nothing being held constant. None of the variables are being held constant. So this is a constant. This constant is one that is universal, and it's for all gases at all temperatures and pressures and under all conditions. And so it gets its own indicator, which is the letter capital R, which is the ideal gas law or the ideal gas constant. If we rearrange this, we get the more familiar form, where we are going to multiply through both sides by N and T, and we get that P times V is equal to N times R times T, which we sometimes refer to as Pivnert. And this is the ideal gas law. The R value, R has a couple of different values depending on what units we choose to use. So the most common unit is going to be 0.08206. And the units here, we'll see how the units get used in a few minutes, are liters times atmospheres divided by moles times Kelvin. And the units are going to be there. They're going to help you to remember what units we need to have our various numbers in. And this is going to be if the pressure is in atmospheres. We can also assign it a value of 8.314, and that's going to be, oh, great, where did it go? Oh, there it is, 8.314, and the units are liters times kilopascals over moles times Kelvin. And these numbers are both on your reference chart. And so the one that you choose is going to depend on whether you have units of atmospheres or units of kPa for pressure. If you have millimeters of mercury, there is another version in the book that you can use, but I don't recommend it because I'm not going to give it to you. So either convert from millimeters of mercury to kPa or atmospheres if you have a pressure in millimeters of mercury, and that way you can get the right answer. All right, so according to the units, the volume must always be in liters. So if I give you milliliters or anything else, we have to convert to liters. The pressure, as I said, in kPa or in atmospheres, convert if you're given millimeters of mercury. The temperature, always in Kelvin. So degrees C are always going to be converting to Kelvin. And the number of moles of the gas is N. And so if you're given grams, convert to moles using molar mass. On the other side, if I ask you to tell me how many grams there are of something, determine the number of moles first. And then from that, determine the number of grams. In these problems, unlike the previous problems, we are always in one set of conditions. So nothing is going to be changing when we use PV equals nRT. All we're going to do is see that we have 3 of the 4 properties of the gas, and we're going to then plug them into, rearrange PV equals nRT, and plug the values in. So I'm going to give you, in this first example, the pressure of the gas is what I'm looking for. So let's make that our question mark. The volume, 10.0 liters. The number of moles is 2.30 moles. R is going to be, because I asked for units of atmospheres, I'm going to use 0.08206 liters times atmospheres over moles times Kelvin. Yes, please do put in those units. That way you'll be sure you get the right answer at the end. And finally, the temperature, 75.0 degrees Celsius, but we have to add 273 to that and come up with 348 Kelvin. So don't forget, convert, alert. Always make sure you do that conversion. Now that we have our 3 properties plus the R value that we want, we're going to rearrange PV equals nRT to solve for P. So we're dividing both sides through by V. And we get that P is equal to N times R times T divided by V. Now we plug the numbers in. N is 2.30 moles. R 0.08206 liters atmospheres divided by moles times Kelvin. The temperature was 348 Kelvin, and all that divided by 10.0 liters. So why don't you go ahead and run that calculation through your calculator for a moment, and pause for a moment, and then come back. So I hope you calculated that, and let's see if we all got the right answer. First, let's look at units. In this, we're going to cancel moles in the numerator with moles in the denominator of the unit. By the way, only plug the numbers in once. Don't plug the numbers into the units of R. This is units only. No numbers. Let's see. K cancels out with K. The liters cancel out with liters, and that leaves us with ATM. And the answer then in atmospheres is 6.57 atmospheres. I hope you got the right answer. As I said before, given the grams of the mass, you'd convert to moles using the molar mass. And if grams are wanted, we'd calculate N and then convert to grams, again, using molar mass. Now, one of the cool things about PV equals nRT is that this now gives us a tool for determining the molar mass of a gas if we know the density of the gas. So, given the density of a gas, if we're given the density in the units of grams per liter, since we're not going to be given a volume, let's assume that we have 1 liter. It's just going to make life easy for us, and as long as we only make one assumption like this, it's going to be valid. So we have 1 liter of the gas. Otherwise, if I give you a density in terms of number of grams in number of liters, then you can also use that. Otherwise, once you've got that, the pressure and the temperature will be given. And so then the unknown in the ideal gas law is going to be the number of moles. And then to calculate the molar mass is just grams over moles. And so you'll be given the density of 1 liter, and you're going to calculate the moles. So the density is just going to be equal, as the grams is just going to be equal to the mass divided by N. So whatever the mass was in the density. And on the homework, I've broken this up into 2 problems to help you out. So we want to know what the molar mass of a gas is with a density of 8.0 grams per liter, pressure of 450 kilopascals, and 298 Kelvin. Yay, no conversions needed there. So we're going to assume 1 liter, and let's just put a couple of sig figs there. 3 sig figs should be enough since that's what we have there. Assume 1 liter, and so we have 8.00 grams when we get to that part of it. The pressure, as we noted, was 450 kPa. The volume, 1.00 liters. The number of moles of gas, that's our unknown. That's what we need to figure out. R is, since we're in kPa, we're going to use 8.314 liters times kPa divided by moles times Kelvin. And finally, the temperature, no conversion needed. I gave you Kelvin, 298 Kelvin. By the way, you do have to watch out for volumes that need to be converted from milliliters into liters. Make sure you do that as well on the homework. Looking at PV equals nRT, N is our unknown. So we're going to divide through both sides by RT and find that N is equal to P times V over R times T. And that equals 450, and let's put the decimal point there for precision, kilopascals, volume 1.00 liters, R was 8.314 liters times kPa divided by moles times Kelvin, and the temperature 298 Kelvin. That should get us our answer. Go and calculate your answer for the number of moles. Stop the video and then come back when you're done. Before we do that calculation, let's take a look at the units. So we have kilopascals on top, kilopascals on the bottom. We have liters in the numerator, liters in the denominator. In the denominator, we have Kelvin over Kelvin. And that leaves us with moles in the denominator of the denominator. Now, as you may recall from math, if we have something in the denominator of the denominator, multiplying through by moles over moles, we'll cancel out the moles in the denominator and leave us with moles as our unit up on top, which is what we're looking for. And when you do the math, we get 0.182 moles of this gas. We don't know what the gas is, so we can't identify it yet. Now that we have the moles, we can find the molar mass. As we said up above, we have 8 grams of the gas, so we're going to bring 8 grams down here. We're going to divide that by 0.182 moles. Notice we have the units we need, grams over moles. So stop the video and do the calculation. And when you do that calculation, we get 44.0 grams per mole as our answer. And if I gave you some gases, you could determine which one it is. 44 grams per mole is probably carbon dioxide, but it could be others as well. All right, so remember, if you're given the molar mass, the other way works as well. To find the density, if given the molar mass in grams per mole, now assume that N is equal to 1.00 moles, and you're going to find the volume. You're going to look for the volume, and then the density is just going to equal the grams divided by the volume, and that's going to be in grams per liter. Now, if you're a little more industrious, and some of you have been reading the book, you'll find on pages 437 to 438 in the book, there's another equation that they derive, PM equals DRT, where M is the molar mass, and D is equal to the density, and the density is in grams per liter. And if you want to try out that equation and use it to convert between molar mass and density, so that will allow you to convert between molar mass and density directly, you can do it. However, make sure that you test that out and are comfortable doing it before trying to use that on any test or quiz. Okay, so that's it for the ideal gas law. Please go and do the homework, and I will see you next time.